Solving a triangle given two sides and an opposite angle, SSA. This is the hardest case there is, the SSA case. We call it the ambiguous case, and here is why. Let's say we knew angle alpha, so we were given that measurement. Let's say we also knew side B, and then we know one other side, not that side on the bottom. We don't know how long that is. That would be SAS, where the angle we know is in between the two sides. This is SSA, so the side we know is this other side that belongs over here. Well, let's call that side A. It would be opposite of angle alpha. Here's the problem. Depending on how long side A is, lots of things can happen. If I take this and I try to make a triangle using this length, I can't do it. I can swing this around however I want. It's never going to reach down there to the bottom, which means it's possible to be given an alpha, a B, and an A that doesn't even make a triangle. It's possible that there is no triangle. Of course, if that A side had been a lot longer, if it had been a very long extra side, then I wouldn't have any trouble. I'd come over here, I'd attach it, I'd need to swing it around so as to land on that bottom piece there, but I would make one triangle, and I could solve for the other angles and sides. But here's the strangest situation. What if A isn't super short or super long? What if it's kind of in between? Well, if I bring this over here, of course I can certainly swing it around and make a triangle, but I could also swing it around on this side and make a second triangle. In other words, that same length can be used to generate two different triangles. Alpha is still the same, B is still the same, but you could make this little triangle with side A or this bigger triangle with side A. In other words, two triangles are possible. Well, when you're given this SSA case, it's hard to know which of these situations is going to happen at the beginning of the problem. And so here's what we'll do. We will expect two sets of solutions. In other words, when we see SSA, we'll figure, oh, this is that ambiguous case. I bet we're going to get two triangles. We'll start solving. If it turns out to be one of the other situations where there's only one triangle or where there is no triangle at all, we'll figure that out during the solving process, and that will become clear during the examples. Okay, let's look at an example problem. We are given three pieces of the triangle, A, B, and alpha. We want to find the remaining three. Drawing a sketch is always a good place to start. Let's see, I've got angle alpha. I'll put that here, 20 degrees. I've got side B, which is 40, and then side A. Side A has to be across from angle alpha, and so I have to put the 30 right here. Let's label the missing pieces. Let's see, beta has to go opposite B, and that leaves this for angle gamma and down here for side C. So my job in this problem is to find angle beta, angle gamma, along with side C. This is an SSA problem. I have two sides, and the angle that I know is not in between the two sides. It is opposite one of the sides. That's SSA. And I know that this is the tricky case. This is the ambiguous case. So already at the start, I'm anticipating something strange may happen. So where should I start? Well, I only know one angle, but I do see that I have a complete pair, right? An angle with its opposite side. So that makes me think I should be able to use the law of sines. Do I have half a pair? Yeah, here's side B. I don't know angle beta, but if I use the version of the law of sines that says sine alpha over A equals sine beta over B, I know three of those four pieces. I can solve for the fourth. I would have sine 20 degrees over 30 equals sine beta, I don't know beta, divided by 40, the B. Well, let's cross multiply. That'll give me 30 sine beta equals 40 sine 20 degrees. And then divide both sides by 30, and I've got sine beta equals that number. I can get a decimal version of that number on the calculator. Let's see, I am in degree mode, so I'm good to go there. I'm typing in 40 sine 20 and then divided by 30 for a value of about 0.456. Okay, now here's the critical part. I have sine beta equals 0.456. That's a trig equation, and I need to remember that trig equations have lots of solutions. Now, I don't need to find all the solutions. Thankfully, beta is an angle in a triangle, which means it can only be between 0 and 180 degrees, but I do need to find any angle in that range that is a possibility, which means I'm going to have to draw a picture. That's how we find solutions to trig equations. Sine is positive in both the first quadrant as well as the second quadrant. There is a nice first quadrant angle here whose sine ratio is 0.456. If I really wanted to draw that out, I could write 0.456 over 1, opposite over hypotenuse. There is also a second quadrant angle that has the same sine ratio, 0.456 over 1. I need to write down both possibilities. Remember the SSA, I'm already expecting that I'm going to get two sets of answers here. Let's see what happens. How would I obtain those answers? I'll call the little one beta 1. Beta 1, that is super easy. All I have to do is take the sine inverse of our 0.456 number. Again, I can do that right on the calculator. In fact, I'll use the whole thing. Try not to round in the middle of these problems. So I'll use sine inverse of my last answer to give me about 27.1 degrees. What about beta 2, the larger red angle, the angle in the second quadrant? Well, it's all about symmetry. If this little thing is about 27.1, then of course this angle is the same, 27.1. And I can see then that the red angle would simply be 180 degrees minus beta 1. In other words, minus that 27.1 degrees. Again, we can get it right off the calculator. The 27.1 was the last answer, so I'll do 180, take away my last answer, and that's about 152.9 degrees. We are saying here there are two sets of answers. Look back at the picture. I didn't really know how long I was supposed to make side C. I didn't know how long that was. I did know that this was a 20-degree angle, and I did know the 40, but when I drew on that 30 side, I drew it over here. And that created an acute angle for angle beta. You can see that it's less than 90 there. That must be the 27.1 degrees. But you see, I could have swung it around this direction instead. And if I had, then angle beta, which would be right here, would be an obtuse angle, apparently 152.9 degrees. The point is, I have two possible triangles, so I have to give two sets of answers. Gamma 1, beta 1, and C1, and then gamma 2, beta 2, and C2. The work isn't hard, I just need to do everything twice. For gamma in each case, well, I know all the angles in the triangle add up to 180. So, for example, to find gamma 1, all I would have to do is add up the other two angles and subtract that from 180 degrees. What do I know? Here's the one we're calling the first triangle. Let's see, one of the angles is 20, and beta 1 was 27.1. And you can check on the calculator, this comes out to be 132.9 degrees. Gamma 2, I would just do the same thing, but for the other triangle. In that triangle, still, the first angle is 20 degrees. And then the other angle, angle beta, beta 2, was 152.9. And again, from the calculator, I get 7.13 degrees. I know my pictures aren't perfect, but you can tell that certainly in triangle 1, the gamma angle is a little bit bigger, whereas in triangle 2, gamma 2 is a very, very small angle, 7.13 degrees. Okay, so we know all the angles. All that's left is to find side C, the two different versions. Obviously, this one is going to be a little on the longer side, and in this triangle, it's a little shorter. How will I do that? I'll have to use the law of sines. I still have that complete pair, sine alpha over A, so I can still say sine 20 degrees divided by 30, just like we did before. And that's going to be equal from the law of sines to sine gamma, whichever gamma I'm talking about, divided by C. Let's do the algebra, and then we'll fill in our two parts. I can cross multiply, which gives me C times sine 20 degrees equals 30 sine gamma. C is what I'm interested in finding here, and so I end up with C is 30 sine gamma divided by sine 20 degrees. Well, all I have to do to get C1 and C2 is put in my two different gammas. So C1 will be 30 sine gamma 1 over sine 20 degrees, and C2 will be 30 sine gamma 2 over sine 20 degrees. And then we'll go to the calculator to work these things out. By the way, here are the calculations I did for the two gamma angles. You always want to keep your digits long in the calculator. You don't want to round anything in the middle of the problem, especially if you're going to be using these numbers in a later calculation. So you can see here's the 132.9, here's the 7.13, or I probably should have just rounded it to 7.1 to be consistent. Okay, in order to find C1, I need to take 30 sine gamma and divide it by sine of 20 degrees. So I'll type 30 sine, okay, gamma is that 132.9 number. I'm going to arrow up to it and choose it so that I'm using the entire value and not my rounded value. And then I want to divide that by sine 20. And I get 64.3 approximately. Well, that would be C1. The C on triangle 1, the longer C, is about 64.3. If I want to get C2, I do the same thing again, this time with gamma 2. So 30 sine gamma 2 is that 7.1310 angle. I'll choose that. I'm not using a rounded value. I'm using that whole value so that I won't be off any at the end. And then I need to divide that also by sine 20. And I get about 10.9. So C2 is about 10.9. Again, we were expecting that C2 was going to be a much shorter side in that second triangle. And we have finished the problem. We've given the two possibilities for angle beta, the two possibilities for angle gamma, and the two possibilities for side C. The steps that we took are the typical ones to take when you have this SSA situation. Thanks for watching.